Hey there, science fans! Today, we're diving into something super cool, something that might sound a bit like math class. But trust me, it's at the very heart of doing amazing chemistry. We're talking about statistical tests. Now, why would a chemist, busy mixing potions and understanding molecules, need statistics? Well, imagine you're a detective, but instead of solving crimes, you're solving the mysteries of matter. Your clues are the numbers you get from your experiments, measurements of mass, volume, concentration, reaction rates, all sorts of things. Statistics, my friends, is like your magnifying glass, your fingerprint kit, and your DNA analysis all rolled into one for those numbers. It helps you see patterns, make smart decisions, and be confident in your conclusions. When you run an experiment, you're trying to answer a question. Did this new catalyst speed up the reaction? Is the amount of iron in this water sample safe? Does this new drug formulation actually work better? You get data, but that data always has a little bit of, wiggle. Statistical tests are the tools that help us sort through that wiggle, that variability, and figure out what's a real effect and what's just random chance. It's all about turning raw data into real knowledge, and that, my friends, is what science is all about. Get ready, because numbers are about to get exciting. All right, let's get friendly with our first statistical superstar, the student's t-test. Now, the name student might make you think it was invented by, a student, and you'd be sort of right. It was developed by a brilliant chemist and statistician named William Seeley Gossett while he was working at the Guinness Brewery in Dublin, Ireland, way back in the early 1900s. Funny enough, because of company policy, in order to publish his findings, he had to do so under a pseudonym, or in other words, a pen name, and he chose student. Thus, the test became known exclusively under the pen name he chose for himself rather than his actual one. By the time he left the company, the damage had been done. People around the world became acquainted with the student t-test rather than his proper name. How tragic? So this powerful test, used worldwide, comes from the world of brewing better beer. How cool is that? And what's the purpose of the student t-test? How can this help us statistically? Its main job? To help us compare the average values or means of one or two small sets of data when we don't know the true standard deviation of the whole population. The core idea behind the t-test is to figure out if the difference between two means is statistically significant. In plain English, that means, is the difference we see real, or could it have just happened by random chance? Imagine you've developed a new fertilizer, and you test it on a batch of plants. The t-test helps you decide if your fertilizer actually made a difference, or if the height variation is just normal plant-to-plant activity. The student's t-test isn't a one-size-fits-all tool. It actually comes in a few different flavors, or cases, depending on what exactly you're trying to compare. Understanding these cases helps us pick the right version of the test for our specific chemical question. The first case is when we want to compare the mean of a single sample to a known or accepted value. Imagine you've bought a certified reference material, say a solution that's supposed to have exactly 10.00 parts per million ppm of lead. You run several analyses on it. The t-test can help you determine if the average of your measurements is significantly different from that certified 10.00 ppm value. The second case is probably the most common, comparing the means of two independent samples. Independent here means that the measurements in one sample don't affect the measurements in the other. For example, you might be comparing the yield of a chemical reaction using two different catalysts, Catalyst A and Catalyst B. You run several trials with Catalyst A and several with Catalyst B. The t-test for two independent samples helps you decide if there's a statistically significant difference in the average yields produced by the two catalysts. This case often has a further subdivision based on whether we can assume the variances, a measure of data spread, of the two samples are equal or unequal. If you like learning about chemistry for fun, or regardless of why you clicked on this video, subscribe. I will provide a link to the textbook down in the description below. This textbook is the source of all my videos and lectures, and where the information comes from for my analytical chemistry videos. Let's continue back to the lecture. Now, calculating t-statistics and p-values by hand using formulas and statistical tables can be done, and it's a great way to understand what's happening under the hood. But let's be honest, in the hustle and bustle of a modern lab, it can be a bit time-consuming and, dare I say, prone to calculation errors if you're not careful. That's where our trusty digital lab assistants come in, spreadsheet programs. Software like Microsoft Excel or Google Sheets are incredibly powerful tools for chemists, not just for organizing data, but also for performing statistical tests like the student's t-test quickly and efficiently. They take the computational grunt work out of the equation, letting you focus on interpreting the results. Most spreadsheet programs have built-in functions specifically designed for t-tests. For example, in Excel, you might use the function. This function typically asks you for a few key pieces of information: the range of data for your first sample, the range of data for your second sample, if applicable. Whether it's a one-tailed or two-tailed test, we usually use two-tailed unless we have a very specific directional hypothesis, and the type of t-test to perform, paired, two-sample equal variance or two-sample unequal variance. Once you provide this information, the spreadsheet does all the complex calculations in the blink of an eye and gives you the p-value directly. Spotting the odd one out, introducing the Grubbs test. Every now and then, when you're diligently collecting data in the lab, you might get a result that just looks weird. It's way higher or way lower than all the other measurements you've taken for that same sample under the same conditions. This kind of odd one-out data point is called an outlier. Outliers can be a real headache because they can skew your average, inflate your standard deviation, and potentially lead you to incorrect conclusions. But before you just decide to ignore it because it doesn't fit your expectations, science demands a more objective approach. That's where the Grubbs test, sometimes called the ESD, Extreme Studentized Deviate Method, comes to the rescue. The Grubbs test is a statistical procedure specifically designed to help you identify a single outlier in a dataset that is assumed to come from a normally distributed population. Think of it as a statistical detective that sniffs out the most suspicious data point. Grubbs test in action, an outlier example and keynotes. Let's make the Grubbs test more concrete with a quick example. Suppose you're determining the percentage of chloride in a sample, and you perform 5 replicate analyses, getting the following results: 30.5%, 30.8%, 30.6%, 31.5%, and 30.7%. That 31.5% value looks a bit higher than the others, doesn't it? It's our suspect. First, we calculate the mean of these 5 values, which is 30.82%. Then we calculate the standard deviation, which turns out to be approximately 0.396%. Now we calculate our G statistic for the suspect value, 31.5%. G equals the absolute value of 31.5 minus 30.82 divided by 0.396, which is approximately 1.717. Next, we need the critical G value. For a sample size of 5 and a significance level of 0.05, the critical G value from a table is approximately 1.672. Now we compare our G underscore calculated, 1.717, is greater than G underscore critical, 1.672. Ding, ding, ding. According to the Grubbs test, we have statistical grounds to consider 31.5% an outlier. This doesn't automatically mean we throw it away, but it flags it for serious scrutiny. Drawing the perfect line. The method of least squares. All right, let's switch gears and talk about something incredibly useful in chemistry, especially when we're trying to figure out the concentration of an unknown sample calibration curves. To make a good calibration curve, we need to draw the best possible straight line through a set of data points. But how do we decide what the best line is? Do we just eyeball it? Well, we could, but our eyes can be deceiving, and science loves precision. This is where a wonderfully elegant mathematical technique called the method of least squares comes into play. It's the gold standard for fitting a line to experimental data. Imagine you've prepared a series of standard solutions, each with a known concentration of a substance you're interested in. You then measure some property of these solutions, maybe how much light they absorb using a spectrophotometer or their electrical conductivity. You plot these measurements on the y-axis against their known concentrations on the x-axis. Calibration curves from standards to unknowns. So, we've learned about the method of least squares, the mathematical engine that helps us draw that perfect line. Now, let's put it into practice by building and using a calibration curve, a true workhorse in analytical chemistry labs. The first step is meticulous preparation of your standards. You need a series of solutions with accurately known concentrations of the analyte, the substance you want to measure. Typically, you'd prepare at least 5 or 6 standards that bracket the expected concentration range of your unknown samples. Accuracy here is paramount, as the quality of your calibration curve, and thus your unknown results, depends entirely on how good your standards are. Once your standards are ready, you measure the instrumental response for each one. The power of numbers, confidence in chemical discoveries. And there we have it, a whirlwind tour through some of the essential statistical tools that empower chemists every single day. We've seen how the student's t-test acts as a discerning judge, helping us compare experimental results and decide if observed differences are truly meaningful or just whispers of random chance. We explored its different faces, whether comparing a sample to a known value, contrasting two independent methods, or looking at changes within the same samples using a paired approach. We even saw how spreadsheets can be our trusty sidekicks, making these calculations swift and accessible, letting us focus on the science. We then ventured into the world of data scrutiny with the Grubbs test, our statistical detective for unmasking those pesky outliers. It provides an objective way to flag data points that seem out of sync with the rest, prompting crucial investigation before we make decisions about including or excluding them. Remember, it's not just about finding the outlier, but understanding why it might have occurred. This careful handling of data ensures the integrity of our conclusions. Like and subscribe. Make sure to share if you found this useful. Be sure to have a nice night, and good night.